Welcome to Module 4, Chapter 12, on the role of life cycle assessment in the circular economy. In this chapter, we will explore how life cycle assessment, or LCA, serves as a foundational tool for evaluating the environmental impacts of products and systems throughout their entire life cycles. LCA is essential for guiding the transition from traditional linear models, where resources are used and discarded, to circular models that prioritize reuse, recycling, and sustainability. We will discuss how LCA helps identify opportunities to reduce environmental impacts in various sectors, such as construction, manufacturing, and consumer products. By understanding the strengths and limitations of LCA, we can better appreciate its role in supporting circular economy strategies and making informed decisions that benefit both businesses and the environment. This chapter will provide a comprehensive overview, practical examples, and insights into how LCA drives sustainable change. In this chapter, we will begin with an introduction to the main concepts and definitions of life cycle assessment and the circular economy. We will then discuss the methodological considerations and adaptations required when applying LCA to circular systems, focusing on the unique challenges these systems present. Next, we will examine how LCA is applied across different stages of the circular economy life cycle, including design, production, use, and end-of-life phases. We will address the challenges and limitations of using LCA for circularity assessment, such as data quality and the integration of social and economic dimensions. The chapter will also cover how LCA can be combined with circularity indicators and other assessment tools for a more comprehensive evaluation. Finally, we will look at real-world case studies from business contexts to illustrate practical applications, and we will conclude with a summary of LCA's role in supporting circular economy strategies. Life cycle assessment is a comprehensive framework for evaluating environmental impacts throughout the life cycles of products and systems. Its role in the circular economy is to guide the transition from linear models, which focus on single use and disposal, to circular models that emphasize reuse and sustainability. Methodological considerations are crucial, as adaptations are needed for multi-life cycle systems to ensure accurate assessments. Standard LCA techniques are applied, but they must be tailored to address the complexities of circular systems. LCA is practically applied in the initial design and production phases, as well as in end-of-life management, to optimize environmental performance. Challenges include integrating LCA with other tools and addressing limitations such as data quality and system complexity. Real-world case studies demonstrate how LCA supports business decisions and helps organizations implement effective circular economy strategies, making it a vital tool for sustainable development. Life cycle assessment plays a vital role in the circular economy by evaluating the environmental impacts of products and services across different sectors. In the building sector, LCA helps decrease embodied greenhouse gas emissions by promoting strategies like reusing materials and optimizing energy-intensive components. In manufacturing, LCA supports the development of circular business models by quantifying environmental impacts and preventing unintended problem shifting. For consumer products, LCA considers real user behavior and displacement effects to accurately assess the benefits of reuse. In the context of lithium-ion battery remanufacturing, LCA demonstrates the environmental advantages of second-life batteries compared to new ones, emphasizing the importance of avoided production emissions. By providing insights into environmental impacts and supporting the development of circular business models, LCA enables organizations to make informed decisions that enhance sustainability and resource efficiency across various industries. Applying life cycle assessment to circular economy systems requires specific methodological adaptations. One major challenge is defining functional units that reflect multiple life cycles and cascading uses, rather than traditional single-use metrics. Advanced frameworks like circular life cycle sustainability assessment integrate LCA with life cycle costing and social LCA to provide a holistic view of sustainability. These approaches address environmental, economic, and social dimensions, and are increasingly used in sectors such as construction. Indicators like the Material Circularity Indicator and Product Circularity Indicator help evaluate circularity performance across multiple life cycles. By adopting integrated approaches, organizations can better assess the sustainability of circular products and services, ensuring that environmental, economic, and social impacts are considered. This comprehensive assessment is essential for supporting the transition to a circular economy and achieving long-term sustainability goals. Effectively modeling end-of-life scenarios in circular systems involves innovative allocation approaches to distribute environmental impacts across multiple cycles. European standards such as EN 15804 and EN 15978 provide methodologies for environmental product declarations and building performance assessment. The cut-off approach is suitable for open-loop systems, while the linearly digressive approach works for closed-loop systems, both aligning with circular economy principles and incentivizing circular practices. Modeling must also account for changes in material properties over multiple cycles, which can significantly affect environmental performance. Iterative modeling approaches are used to address these shifts, ensuring that the assessment accurately reflects the realities of circular systems. By following these standards and approaches, organizations can better evaluate the environmental benefits and trade-offs of circular strategies, supporting sustainable resource management and the development of effective circular economy practices. Choosing between attributional and consequential life cycle assessment approaches is crucial in the circular economy. Attributional LCA provides a static snapshot of current impacts, focusing on the direct environmental effects of products and processes. Consequential LCA, on the other hand, considers broader market effects and future scenarios, assessing the potential impacts of decisions on interconnected systems. Defining system boundaries carefully is essential, especially for complex products, to ensure all relevant processes and impacts are included. This distinction helps optimize material recovery and reuse within defined boundaries, supporting circular economy goals. Integrating upstream design strategies, such as designing for circularity and durability, enables reuse, repair, and remanufacturing capabilities. By selecting the appropriate LCA approach and clearly defining system boundaries, organizations can enhance the effectiveness of circular strategies and achieve more sustainable outcomes. Managing the environmental and sustainability performance of circular products requires a comprehensive approach. This involves using robust assessment frameworks like Circular Life Cycle Sustainability Assessment and Life Cycle Sustainability Assessment, which combine environmental, economic, and social evaluations. Innovative design strategies, such as designing for circularity and durability, are incorporated to enhance product longevity and reuse. Methodological considerations include utilizing appropriate allocation methods for circular flows, tailored to the complexities of circular systems. Accurate assessment is vital for evaluating sustainability performance and providing science-based support for the transition to a circular economy. By adopting comprehensive approaches, organizations can ensure that all aspects of sustainability are considered, leading to more effective and resilient circular strategies that drive long-term environmental and economic benefits. The design phase is a critical stage where life cycle assessment guides eco-design principles and encourages the integration of circularity features into products and systems. By applying LCA early in the design process, we can identify opportunities to enhance durability, repairability, recyclability, and modularity. These features are essential for promoting circularity and extending product lifespans. In the construction industry, strategies such as design for disassembly and modular construction have been shown to significantly reduce environmental impacts, making buildings easier to adapt, reuse, or recycle at the end of their life. In the electronics sector, LCA helps prioritize design for recycling features and the selection of environmentally friendly materials, supporting the development of products that are easier to reuse and recycle. By focusing on these circularity features during the design phase, organizations can create products that support sustainable resource management and contribute to the transition towards a circular economy. During the production and use phase, life cycle assessment is applied to assess the environmental performance of new business models and maintenance activities. LCA helps organizations evaluate the impacts of different production and use models, revealing opportunities for substantial carbon emission reductions. For example, in the furniture industry, strategies such as incorporating on-site photovoltaic cells for energy generation and reducing forklift usage within facilities have been shown to significantly lower carbon emissions. LCA also evaluates the effects of maintenance and repair activities, which are essential for extending product lifespans and improving sustainability. By identifying and implementing effective strategies during the production and use phase, organizations can reduce their environmental footprint, enhance resource efficiency, and support the development of circular business models. These findings highlight the importance of evaluating production and use models to identify opportunities for improving sustainability and extending product lifespans. Life cycle assessment plays a crucial role in the end-of-life phase by evaluating the environmental benefits and trade-offs of circular options such as remanufacturing, recycling, and composting. LCA compares these circular strategies with linear disposal methods like landfilling and incineration, helping organizations understand the potential environmental impacts of different end-of-life scenarios. The cut-off method is particularly suitable for assessing end-of-life scenarios within circular systems, as it helps define appropriate technical boundaries for recycled or recovered materials. By using LCA to evaluate end-of-life options, organizations can make informed decisions that support sustainable resource management and reduce environmental impacts. This phase is critical for understanding how circular strategies can contribute to sustainability and for identifying the most effective approaches to managing products and materials at the end of their life cycle. At the system level, life cycle assessment provides tools to assess the overall environmental performance of entire value chains and industrial symbiosis networks. A holistic perspective is needed to identify potential trade-offs between improvements in material circularity and impacts on environmental, economic, and social pillars. LCA enables organizations to evaluate complex systems, balancing material circularity with environmental impacts and considering economic and social dimensions. By integrating these aspects, LCA supports sustainable development and enhances the circular economy framework. System-level assessments are essential for understanding the broader implications of circular strategies and for ensuring that sustainability goals are achieved across entire value chains and networks. Applying life cycle assessment for circularity assessment faces challenges such as data availability and quality issues. There is often a scarcity and inconsistency of data on circular flows, making it difficult to model multiple life cycles, remanufacturing processes, and secondary material quality. The complexity of circular systems and the need to integrate broader sustainability dimensions further complicate the assessment. Traditional LCA frameworks are designed for linear processes and may struggle to accommodate the dynamic and interconnected nature of circular systems. To overcome these challenges, organizations must develop more robust data collection and modeling approaches, ensuring that assessments accurately reflect the realities of circular systems and support effective decision-making for sustainability. Traditional life cycle assessment has historically focused on environmental impacts, often neglecting social and economic dimensions. Comprehensive assessment requires considering all aspects of sustainability, including indirect, diverse, and long-term impacts. Current frameworks like life cycle sustainability assessment and circular life cycle sustainability assessment aim to integrate these dimensions, but more robust methodologies are needed to fully capture the consequences of circular strategies. Addressing spatially diverse and long-term impacts is challenging, and overlooking social and economic factors can limit the effectiveness of circular economy initiatives. By developing and adopting more comprehensive assessment methods, organizations can ensure that circular strategies support broader sustainability goals and deliver lasting benefits. The dynamic nature of circular systems and rapid technological innovation pose challenges for life cycle assessment studies. Conventional LCAs often assume static systems and immediate technology adoption, overlooking gradual innovation diffusion, infrastructure changes, and stock dynamics. This limits their ability to predict long-term sustainability impacts and environmental consequences of future circular economy scenarios. To address these limitations, organizations must develop dynamic and prospective LCA models that account for temporal changes and evolving system characteristics. By considering the dynamic nature of circular systems, LCA can provide more accurate and relevant assessments, supporting informed decision-making and the successful transition to a circular economy. To enhance the utility of life cycle assessment for circular economy assessment, there is a need for continued development of prospective and dynamic LCA models. These models better capture temporal aspects and the evolving nature of circular systems, providing more accurate and relevant assessments. Integrating LCA with life cycle costing and social life cycle assessment is essential for a holistic sustainability view. Advancements in methodology and data availability are crucial for making informed decisions and fostering a successful transition to a circular economy. By developing and adopting improved assessment frameworks, organizations can support sustainable development and achieve long-term sustainability goals. Integrating life cycle assessment with circularity indicators is crucial for evaluating both environmental impacts and circularity performance. Circularity indicators measure material flow loops and resource efficiency, while LCA quantifies environmental impacts. This integration ensures comprehensive evaluation within the circular economy, providing environmental validation and helping prevent unintended environmental burdens. By combining these assessment tools, organizations can develop effective circular strategies that support sustainability and resource efficiency. The integration of LCA and circularity indicators is essential for achieving comprehensive and robust assessments, supporting the development of successful circular economy initiatives. Examples from various sectors show the power of combining life cycle assessment with other tools. In recycled aggregate concrete, LCA and circularity index optimize recycling processes and highlight both economic value and environmental impact, such as identifying transportation as a major emission source. In the plastics industry, LCA and material flow analysis assess environmental impacts and recycling rates, while urban projects use LCA, material flow analysis, and the material circularity indicator for a holistic environmental view. These sector-specific examples demonstrate how integrated assessment approaches can support the development of effective circular strategies and enhance sustainability across different industries. Frameworks like Circular Life Cycle Sustainability Assessment integrate life cycle assessment with life cycle costing and social life cycle assessment, along with dedicated circularity assessment methods. This approach addresses multi-dimensional sustainability in the circular economy, balancing environmental, economic, and social impacts. Harmonizing diverse methodologies and indicators is challenging but essential for informed decisions in circular economy implementation. By adopting integrated frameworks and systematically selecting appropriate indicators, organizations can rigorously assess environmental targets and ensure broader sustainability in the circular transition. Indian businesses are adopting circular practices for competitive advantages such as enhanced resource efficiency, cost savings, and access to green markets. Life cycle assessment helps evaluate these initiatives, especially in plastic waste management, by quantifying environmental benefits and aiding business decisions and compliance with regulations. Investments in infrastructure for collecting and processing plastic are compared using LCA, which assesses the benefits of mechanical or chemical recycling versus linear disposal. Environmental metrics provided by LCA support sustainability reporting and build brand value around sustainable products, helping businesses transition to greener markets and meet evolving regulatory requirements. In Thailand, life cycle assessment is crucial for export-oriented industries facing rising global demand for sustainable production. LCA informs business strategies related to the circular economy, particularly in the packaging sector. Food and beverage and consumer goods industries use LCA to evaluate the environmental performance of circular packaging designs, such as the use of recycled PET in bottles and packaging designed for easier recyclability or reuse. LCA results support sustainability reporting, enhance environmental transparency, and improve competitiveness in international markets. By adopting circular packaging designs and using LCA to assess their impacts, Thai companies can meet global sustainability standards and strengthen their market position. Life cycle assessment is not just an environmental reporting tool. It is a strategic instrument that helps businesses make informed decisions. By quantifying environmental consequences, LCA provides evidence for investment decisions, validates sustainability claims, and supports risk management. LCA enables businesses to manage risks and transition to circular operating models, building a strong business case for circular strategies. These case studies from India and Thailand show how LCA supports the development of sustainable business practices, enhances competitiveness, and drives the transition towards a circular economy. By using LCA as a strategic tool, organizations can achieve long-term sustainability and business success. Thank you for your attention throughout Chapter 12. We have explored the critical role of life cycle assessment in supporting circular economy strategies, covering key concepts, methodological adaptations, practical applications, and real-world case studies. As we move forward, the next module will build on these foundations, introducing new topics and insights to further enhance your understanding of sustainability and circular economy practices. We look forward to welcoming you to the next chapter.